Good afternoon and welcome to Loughborough University's Institute of Advanced Studies. I'm Professor Ksenia Chmut and I'm Director of the IIS. And it's wonderful to see so many of you here today. I was just saying to them that every time I have geography seminar, the kind of full room. So thank you so much for joining us. For those of you online, thank you for joining us as well. As always, we are here today to discuss very exciting, and I'm not sure, boring. Don't think it'll be boring. A really exciting topic. In the last few months, actually, weeks, we've been talking about climate adaptation, climate resilience, kind of naturescapes, and it's really nice to see these topics coming over and over again. So we're really looking forward to Jeff's presentation today. Jeff is our residential fellow. He's with us for a month. Wonderful to have you here. And there will be a formal introduction in a second. Just a couple of housekeeping rules before we start. The seminar is recorded, and the actual presentation will be available online on our YouTube channel and also as our podcast. It'll magically appear on all those channels in a couple of days' time. We will be online for Q&A. So for those of you online, if you have questions, please post them online in that little window on Zoom. We will bring them on the screen, but the Q&A session will not appear in the recording. So please feel free to discuss whatever it is you wish to discuss. For those of you in the room, you will then be served lunch, so you please continue the conversation. No fire drills. We're keeping the door open today, so but it'll make if it's noisy, we'll close it down just to allow for airflow. I think that's about it. So Dan, over to you to introduce Jeff.
Thank you so much. I think it is good afternoon now, isn't it? So good afternoon, everyone. It's a real pleasure to introduce colleague, friend, Jeff, to you all. Delighted he can be here with us in terms of sharing some of the incredible work he's been doing over a number of years. Jeff's an internationally recognised scholar, works in sediment transport, river, coastal morphodynamics, and also into the sedimentary deposits. So those signatures that are left in the rock record over long periods of time. And I'm sure he'll talk through a whole range of this, but also what it might mean for society and resilience and some of the things that Ksenia's just been talking about in terms of adaptation and climate change as well. Jeff is currently an associate professor at Texas Tech in the Department of Geosciences, where he leads a research group looking at all of these sorts of sedimentary processes and how they shape some of the world's most dynamic and interesting landscapes. Jeff's got a strong foundation in field science, but couples that with both experimental and theoretical investigations as well. And his work has spanned the globe. He's doing some incredible work out in the Amazon. I was fortunate enough to work with Jeff in a couple of places in the US and also out on the Yellow River in China. But Jeff's also worked out on lots of work on the Mississippi system as well, and looking at the coastal interactions of that large river system as well. And throughout all of that, it's really looking at those impacts of anthropogenic change, climate change, and what it means for those coastal systems. Jeff's work also reaches, I'm sure he'll colour some of this for us as well, reaches through transdisciplinary connectivity as well, really at the heart of lots of what the IIS is about. His findings of his research have an impact on people, on lives and livelihoods around the world as well, and he collaborates really widely as well, from engineering into the social sciences, into humanities and policymakers as well. So really translating sediment dynamics, sediment transport into actionable knowledge as well. We're really fortunate to have him here with us. I'm really looking forward to his talk and the insights that he'll share with us today. And perhaps most importantly, I'm really interested in what's on the reverse of that sign. Probably says something like, keep out with Jeff, with him being on the other side of the boundary there. But Jeff, over to you, really looking forward to your talk.
Well, thank you very much for that wonderful introduction, Dan. And it's a pleasure to be here. I'm very grateful to Loughborough University and the Institute of Advanced Studies for the opportunity to come out here for a month this summer and spend time. I've had wonderful interactions thus far with colleagues from civil engineering as well as geography, and mixed in between, both students and researchers and professors alike. So it's been a very interesting and thought-provoking set of weeks and discussions that I've been able to embark on. This study that I'm going to present to you today is a work in progress. It's something that I've been collaborating with a master's student who just graduated and is now matriculating into a PhD program, and he's studying under me. That's John Nelson here. This is also in collaboration with two other professors. This is Gaku Tanaka from Hokkaido University in Japan, and Professor Gary Parker, who's emeritus now, but he's at the University of Illinois. The picture that you're looking at here is Cedar Creek, which is in central Minnesota. There's a few things that I want to point out before we get started in our talk today. This creek is approximately 10 to 15 meters in width, and it's variable. You can see it here. The bank lines that you see here are unique insofar as that they are not comprised of inorganic sediment, which is the traditional viewpoint of both stream and river systems around the globe. What they have instead of sediment or inorganic sediment is organic sediment that is built by this vegetal matter that you see here, this tall grass that is growing atop of itself. And so these are what we call peat streams, lacking much in the way of inorganic sediment, traditional sand and mud, and replacing that instead with vegetal matter. That doesn't mean that there's a pure absence of inorganic sediment. In fact, you can see perhaps on the margins here as well as over here, there are topographic highs. And these are bounding bluffs that are built by drumlins and eskers, which are glacial deposits that were made during the last glacial period, roughly 17 to 20,000 years ago. And these drumlin and esker highlands that bound the valley that is now filling with peat are comprised of sand and gravel. So where the river, or the creek in this case, can abut against these high bluffs here, it can acquire some inorganic sediment. And there are a few locations where that comes in, and you'll see why that's important. But this is just to set the framework for y'all here. One last piece, this is a fielded view that I'll show in a few slides, which will be demonstrating what this looks like during winter months. So bear this in mind. Because we're in central Minnesota, this is quite a cold climate for 3 or 4 months a year. Okay, proceeding. Why do we care about peatland systems? If we look at a map for the global distribution of peat, what we find is that it's bound between high and low latitude regions. And that can occur in both the northern and southern hemispheres. So you can see, just looking at peatland cover as a percent, where we go from 0 to 100 as shades of gray up to black, we find that there are peatland settings, for example, in the northern hemisphere, that extend across Alaska, Canada, parts of the northern United States, of course, here in the British Isles, all the way across Scandinavia and Siberia, extending basically across a belt that is contained roughly between 45 degrees north and 80 degrees north. We find as well that there are peatland settings in equatorial regions, so low latitude settings. These function similarly, but have uniquenesses that are different from high latitude systems. We won't get into that today, but we will discuss some of the aspects driving the dynamics in these high latitude peat systems. Peatlands are important critical environmental habitat on Earth. They cover 3% of Earth's land surface. That may seem nominal, but they possess 30% of sequestered organic carbon. So if we just add up the organic carbon as it's distributed across Earth's terrestrial landscapes, despite only covering 3%, they have roughly something close to a third of its organic carbon. So we think about this storage of carbon, essentially what it is it's sequestered atmospheric carbon. The peat itself is built by vegetal matter that goes through a photosynthetic process of building its biostructure, which is eventually buried and sequestered. So in essence, you're capturing CO2 from the atmosphere, burying it and preserving it in perpetuity. The distribution, of course, as I noted, is primarily low and high latitudes with little and mid-latitude regions. Okay, my study, this study that I'm going to present to you today, focuses on high latitude but subarctic peatland settings. Most of these environments developed after the last glacial maximum, timed at about 17,000 years ago. This is a time period when glaciers, continental glaciers, were retreating across North America and Northern Europe. And in their wake, they were leaving behind large deposits of sediment. those deposits of sediment have relief that are expressed in tens to hundreds of meters in terms of how they are variable in their vertical elevation. And in between those deposits, you can create valleys in essence. And those valleys are the locations where we begin to accumulate peat. So in the wake of the glaciers leaving, in essence, the water pooled in these valleys, and in its place came this vegetal matter that began to grow and develop into peatland settings. So in these peatland settings, they are defined as a condition where vegetal deposition, that is the deposition of organic matter, outpaces decomposition through bacterial respiration. So what this results then is the burial of organic sediment and accumulation of this material. The valley will then fill, so the valley over time slowly fills. And global compilation rates of deposition show that this is a very slow process, something on the order of 1/10 of a millimeter to 1 millimeter per year. So basically a meter of peat per 1,000 years. So if we're looking at a complete, 17,000 years since LGM, one would expect only there to be somewhere between 10 and 17 meters roughly at maximum end for their thickness of deposition of peat in any given valley. There are hydrological agents that define peat systems, and you can roughly classify these into 3 entities. The first would be lakes. So this is an example of a lake setting here, where on the margins you're collecting peat, and these can vary in surface area for several hundred square meters to several acres. You also have bog settings, which is shown here, which is essentially lakes but are filling in with vegetal matter. You can see you have dispersed amongst this standing water here is grass that's growing amongst that water. And then finally, we have stream systems. And the streams are important because they connect lakes and bogs and essentially convey water through a valley setting itself. And so you need these streams to essentially convey and convect water through the peat systems that are contained within the valleys themselves. And this, of course, is going to be the focus of our discussion today. There's a word I use here called morphodynamic, and I realize that I'm talking to a diverse audience. So I'll just take a minute here to define this for you. Morphodynamic is just a field of study that looks at the interaction of fluid flow and sediment transport and how those two are coupled. And you can imagine that across most of Earth's surface, whether you're dealing with terrestrial landscapes or subsea landscapes, the movement of fluid and solid is incredibly important. Those interactions are important for driving morphological change. So morphodynamics is just a field of study that looks at these dynamic fluid solid interactions so as to change and sculpt Earth's land surface. So the morphodynamic evolution of peatland streams is a topic that's nearly absent in scientific research. There's 2 reasons for this, as far as I can tell. Peatland streams aren't dynamic over timescales appreciated by society. And what I mean by this is sort of couched in my title. They're boring. They don't move, at least from the observation window of humans. They seem to be rather stagnant. Whereas you can imagine, alternatively, an alluvial river or stream that carries a lot of inorganic sediment is laterally mobile, vertically mobile, and has a lot of dynamic ends to it that can also affect society. But peatland streams, in essence, are essentially well tamed, at least from the human perspective. They also tend to be in remote and isolated regions, so they're not really directly affecting humans, but nevertheless, as we'll see here, they do have a lot of important interactions with the environment. So the state of the art in terms of examining peatland systems, in particular peatland streams, has been looking at their vertical aggradation. And this is captured in a study published by a colleague of ours, Ken Dell, who's a professor at Wageningen University in the Netherlands in 2017. And essentially what he shows is a peat valley in 4 different stages, as you see here, with peat defined in brown and stream and channel deposits defined in red here. In essence, what he describes is a situation where you're filling and aggrading through time these peat valleys. He finds, for example, that the stream itself can aggrade vertically without any lateral mobility. Or in another circumstance, yes, it moves laterally, but then it pins itself onto the bounding wall of the valley itself, and then has nowhere to go but vertically, or grade vertically upward. Other circumstances are that it can essentially move laterally, hit another impingement point and aggrade vertically, or in this case where it looks like we have sort of a disconnect between channel deposits here and here, this would be the case in avulsion where the channel wholesale switches within the valley itself here. So in essence, this is what we as a science community understand and recognize about peatland streams. It misses everything that we like to understand in terms of the physical evolution of these systems that allows us to model this quantitatively, namely the morphodynamic interactions. One last point I want to make here is that the lateral mobility of peat streams, if there is any, is responsible for liberating the vegetal matter that is otherwise on the floodplain itself. This liberation then renders it available for respiration. So in essence, moving the channel laterally, sweeping it across the floodplain of this peat valley system will unlock this vegetal matter and make it available to decomposition and therefore outgassing, thus breaking the sequestration cycle of essentially capturing and harboring that carbon. Alternatively, the vertical aggradation is what actually drives the sequestration of the carbon itself. So you have two end members here, lateral mobility, which is working to respire that peat, and vertical aggregate, that carbon, and vertical aggradation, which is working to sequester that. Okay. Peatland stream migration is incredibly slow, to the extent that with satellite imagery, we find very little to no movement. And this is captured in a series of satellite images that are taken over basically since satellite data became available in the 1980s to modern times of Cedar Creek. And what you can see is that over time, it looks like the position of the stream is held relatively constant. So there's little to no movement in the observable time frame of observation that includes satellite images. So for any stream system, large rivers all the way down to creeks, we define a characteristic timescale of migration. And this is just to say how fast this system can migrate, and it's meant to be independent of the size of the channel. And what we do to characterize this migration timescale is divide the channel width, a length, by the lateral migration, a speed, which pops out a timescale. For peatland systems, to the best of our knowledge, we're dealing with migration timescales. That is how long it takes this system to migrate one channel width on the order of thousands to tens of thousands of years. So 10 and 3 to 10 to the 4 years. This is in stark contrast to traditional rivers that carry loads of alluvial inorganic sediment. And this is a great example from Brazil with the Ucayali River here. In essence, what you see is migration of this channel system over the time frame of the observation window of the satellite images here. You see things like point bar growth and development, cutoffs that are developing here, oxbow lakes, scroll bars, all kinds of morphological indicators that suggest that this river is highly active and mobile across its floodplain. And we think that we assert that the difference between alluvial rivers and peat rivers is the fact that inorganic sediment, in particular sand, is a driving agent for mobility of the channel system across its floodplain. So when we think about rivers, we tend to have this sort of conception in mind. And indeed, if you do a global compilation of timescales of migration for traditional alluvial rivers, you get something that's on the order of 10 years to 100 years, meaning that it takes about a decade to a century for the channel to migrate one of its widths across its floodplain, which is, again, several orders of magnitude lower than what we find for peat streams. Okay, what other differences exist? I've just grabbed a couple of satellite images here that show on the top traditional alluvial rivers that have, of course, oxbow lakes, scroll bars, nice, beautiful sandy point bars, cut banks, all diagnostic of lateral migration across its channel floodplain. And in these lower two panels here, peat streams that we find in Minnesota. So the first thing that kind of comes out is we have this curvy versus jagged stream profile. That is, if we look at how that channel system is, in essence, sinuous across its landscape, it seems that the alluvial channels are much more curvy, whereas these peat streams are much more jagged, meaning they have these sort of sharp bends to them. And likely that is associated with the fact that the alluvial channels are carrying loads of organic sand. There's also, as I've already noted, a difference in the prevalence of scroll bars, point bars between these two systems, as you see here. What this does is lend to some very interesting hydrodynamic operations within peat streams. Traditionally in alluvial systems, and just back up one slide here, where you have flow that's moving through the channel system, there tends to be the high velocity core, what we call the thoweg. The highest velocity of the water flow is impinged on the outer bank line, and the low velocity of the flow itself, laterally speaking, is closer to the bend itself, so within and on the point bar. But if we look at data that are collected from peat stream, we find the opposite effect here. So this is a channel system from Japan that my colleague Tanaka and I worked on several years ago. In essence, again, you're looking at a peat channel, you're looking at a bend segment, so the channel's flowing in this direction and coming this way. And what we've done is collected velocity data across this channel system. And what you find is on the inner bank, the hotter colors here, the reds and the oranges and the yellows, which indicate higher velocity, are essentially on this inner bank, whereas the slower velocities, in fact, are on the outer bank, which again is opposite to traditional alluvial rivers. So right away, we note that there is something fundamentally different in terms of the hydrodynamic conditions between peat streams and alluvial systems. So we have some set of observations and we developed some hypotheses regarding the behavior of peatland streams. So what we're hypothesizing then is this dense vegetation along the bank lines is highly resistant to erosion, limiting the mobility of the channel system itself. With minimal inorganic sediment, namely sand and mud, there is little material to build bars that we know is effective at deflecting the high velocity water flow and creating a scour condition that lends to mobility of the channel. But there must be some alluvial material present within peat channels, because otherwise over time, vegetation would encroach on the channel, in essence, close it off. And we have examples of this in nature. This is quite literally called the Dead River in Minnesota, which is a peat stream or a former peat stream that has been completely closed off. Now, in essence, just sits as a grassy lowland landscape here. So in this case, the peat stream closed through time due to the encroachment of vegetation. So we think there's some amount of inorganic sediment that's necessary to transit through these peat streams to operationally keep them open, but you can't flood it with inorganic sediment like sand. Otherwise, you just transition it into a traditional alluvial river. So there's some sort of, well, what I'll say is Goldilocks condition that defines not too little, otherwise you kill the system, and not too much, otherwise you transit into a alluvial river channel system that allows peat streams to stay operational. Okay, that's sort of a bit of the background. We care about the lateral migration of peat streams, namely because there are a number of studies showing that high latitude regions where we have lots of peat sequestered are experiencing significant environmental change, namely warming of the climate and increased hydrological cycles. What this means is that there's more intense rainfall, there's more intense runoff in the systems itself, and we don't understand to first order how runoff controls the mobility of the streams and therefore the potential to liberate or get stored organic carbon. So the first principle, having a model, quantitative model that defines migration of the peat streams is necessary to even begin to scratch the surface of how an increased hydrological cycle could affect storage of peat in these high latitude settings. There's recent interest in organic carbon sequestration and release from floodplains due to this channel migration habit. Much of this work that has been emerging in our community, both in Europe and North America, has been focusing on alluvial rivers, and little of it has paid attention to peat systems. So the two citations I provide here are recent studies that have come just describing alluvial channels, traditional alluvial channels in high latitude climates, with recognition that migration of these channel systems as it's enhanced with global warming is in fact liberating much of the floodplain sediment. Imperturbations to morphodynamic operations have a significant impact on the storage and release of organic carbon. So I think we've gone through this in essence enough, and that is essentially vertical aggradation stores carbon, lateral migration liberates it. Okay, so towards an understanding of dynamics of peatland streams, we have a set of research goals here. The first is to quantify the mobility habits of peatland channels. And you think this would be a relatively straightforward operation, but it's not, namely because, as I described before, the channel dynamics are on timescales that are much greater than the observation window of satellites and humans for that matter. We want to test the applicability of models that have been developed for alluvial channels to peatland streams. That is, we have loads of models for alluvial river systems that we can use to describe and predict movement of those channels, namely lateral movement, but we don't know if they work for peatland systems. So we're stuck here trying to reconcile whether or not we can take these pre-existing frameworks and apply them to peatland streams. And for that, what we need are loads of field data to constrain model input parameters that are necessary even just to describe the movement of alluvial rivers. Okay, the last piece here is to compare estimates of channel migration between numerical models and observational methods. So you'll see in a moment here how we go about constraining lateral mobility and how we go about building this numerical modeling framework that we can use input data for collected from the field to make a comparison between both observations of mobility and predictions of mobility through physical modeling. Our study site is a location known as Cedar Creek. You can see up there. It's in central Minnesota. This is the state of Minnesota. Sorry, I don't have its proximity in North American map here, but it's central United States, Canadian borders just to the top here. The town of Minneapolis, the largest city in Minnesota, is just to the south here. The catchment for Cedar Creek is outlined in red, highlighted in red here. It's tough to see. It's in the stippled black line with Cedar Creek in blue here. Our study region is here, and I'll just advance one slide where we just examine this stippled region in here. So this is the actual catchment of Cedar Creek. It's not very large. It's, there's 8 kilometers there. So you might get, if you squint your eyes, 24 or 30 kilometers worth of length out of that catchment. I'll point out that the different color schemes that you see here are elevations of the landscape referenced to sea level. They're not mountains that exist here in central Minnesota, right? We're only looking at a difference in this elevation map of 300 to 270 meters. So roughly 30 meters across this landscape of elevation difference. A couple of important things to point out though, this black box is the field of view for our next slide, which is our research focus site. It happens to be in the Cedar Creek Ecosystem Science Reserve, which is sponsored and operated by the University of Minnesota. But what you can find here, if we do a close-up here, is that there are high spots and then there are low spots that exist where this creek is flowing through. And as I mentioned in the introduction here, these high spots represent glacial deposits. They are these eskers and these drumlins comprised of sand that in some cases can extend 15 meters above the adjacent valley floor that you find here. So our Cedar Creek flows from north to south, so from the top of the screen down to the bottom of the screen here. We're going to look at 2 discrete subregions of this. The first is outlined in this red box here, and the second is in this box labeled D here. The important differences between these 2 subreaches that we're examining is that where we have this upstream channel reach here, you can see that the system itself is free from interaction with any of the bounding sidewalls, the valley margins that are comprised of this sand itself. So this system, in essence, besides where it interacts here, is flowing for several kilometers within a bog, within a peat floodplain bog that is devoid of any introduction or any alluvial sediment. Whereas if we go down to the downstream channel reach here, what you find is that Cedar Creek goes through a pinch point, a topographic pinch point here that represents, again, sand and gravelly deposits that are found as glacial deposits. So in essence, there's much more interaction between Cedar Creek and the adjacent bounding topographic bluffs that could introduce inorganic sediment into the system. And we'll see why that's important here momentarily. Just as a bit of overlay here, this is just a satellite image, same field of view for what you see with this digital elevation model here. And then C and D here represent close-up pictures of our two subreaches, upstream and downstream. Okay, so we have a number of efforts that we've pursued in the last 2 years with this study regarding field studies. The first is imagery analysis that compares 8 years of aerial photographs and satellite images to see if there's any purchase point, any foothold we can get in terms of looking at lateral mobility over the time scale of several decades. The second is hydrological data. We've collected for a variety of flow conditions at Cedar Creek. This is necessary to analyze the stress that is applied to both the bed and the sidewalls in order to compare that stress, that fluid stress, to the stress that would be required to liberate peat or otherwise move inorganic sediment like sand. Sediment coring, we've collected loads of sediment cores to assess the composition of both the channel and floodplain material and analyze the relative distributions of vegetal and inorganic material that comprises the valley fill. So you'll see why this is important here momentarily. The added benefit is that this provides, of course, plenty of vegetation that we can use for C14 dating. And I will say, and you'll see here momentarily, time constraints within the system are incredibly important for understanding the dynamics of the channel system. The last piece here are bathymetric data to constrain channel geometry. The most recent survey was just conducted last month. These data are still being processed, so I can't show them to you, but they are necessary input parameters to bound any sort of numerical modeling that one would try to assert to understand the movement of these channel systems. Okay, the first piece here is data mining, where we went to the University of Minnesota Map Library, went down into the bowels of this place and asked the librarian there if he could extract photos from the 1930s that were collected with a bi-wing aircraft with a large camera attached to it, essentially mapping out and taking photographs of the agricultural areas that were all around the state of Minnesota. He had no clue as to why we were interested in looking at these ag field photographs from the 1930s, but he was very helpful indeed and found, you know, within these volumes and volumes and stacks of photos for decades and across the state, was able to unearth a number of these sorts of photos that you see here. Here's my student, John Nelson, and collaborator Gary Parker, looking diligently at these different photographs for these different creek systems across the state of Minnesota. We are lucky that, you know, essentially as soon as we were able to build fixed wing aircraft, that the state of Minnesota decided it was a worthwhile pursuit in the 1930s to attach cameras to them to take these photographs. This is unusual for most states in the US. I don't think aerial photography of landscapes emerged until the 1960s and 70s for most places. But yes, we have this nice deep bench of photographs dating back almost 100 years now. We were able to essentially take those photographs, georeference them in a geographical information system software, and map out the channel center line for our study reaches. So on the left here, we have the upstream study reach, and on the right here, we have our downstream study reach. The colors that you see here indicate the channel center lines for the different sets of data that were collected over a time scale of several decades here. And the first thing that you can see is that in this upstream channel reach, maybe if you squint your eyes a little bit, you can reconcile some mobility from decade to decade here. But I'm going to be truthful to y'all. Within the resolution of this particular sets of photographs, it's probably meaningless. Meaning that this is essentially a stagnated system, and any of these sorts of movements that you see here are just something to do with georeferencing error in the GIS software. Alternatively, if you look downstream, you actually do see some evidence of migration here. This is the downstream channel section, whereas I mentioned prior, the channel system is passing through this pinch point and collecting inorganic sandy sediment. And so if we try to calculate this timescale of migration, which I had presented earlier, is just the channel width divided by mobility, we can't reconcile anything upstream. So we just put a couple question marks there because we have no evidence for mobility. But downstream, we get something that's on the order of 500 to 1,000 years. And that's just based on the variability of both the width and the migration rates that we measure as part of the movement of these channel center lines over roughly 3 decades. Okay, so we're on to something here, maybe 10 to the 2 to 10 to the 3 years in terms of channel mobility for the downstream section. All right. To characterize the hydrology of the system, we presented you a longitudinal study that looks at long-term data that were collected from winter until summer. And so we went out in March, and this is what that field site looks like in March. So I mentioned at the beginning of my talk with my title slide that I'll refer back to a slide that shows what it looks like in the winter. And this is it. It's the same field of view that I showed you at the beginning. Of course, the grass is now buried under snow cover. The creek, interestingly enough, doesn't freeze because it's constantly groundwater fed. And so that water is essentially above 0 degrees Celsius. And so only rarely when you get -40 conditions in Minnesota will you get a thin veneer of ice over top of the creek. But it does stay liquid throughout the year, mostly. We have to build our hydraulic data sets or we have to instrument our the creek to get our hydraulic data sets in the winter. And that's because in the spring, there's a condition called a freshet, which is usually when you get mass melting of snow that's coupled with extreme spring rainfall events that produces the flood conditions that would probably drive morphodynamic activity of the stream itself. So this is just a field shot of my student John, again, out here making survey measurements. You can see you have to put on your warm weather equipment and your snowshoes, come out and work diligently. I'm not gonna lie, March is not a bad time to work there. You get 12 hours of daylight. It's, 0 to 5 degrees Fahrenheit during the day, and it drops below freezing at night, but it's not -30, right? So it works just fine. And so here's John out here working diligently. What we placed were a number of paving stones that had a number of different instruments that were placed upon them. This is what we call pressure transducer, and what this measures is pressure of water that converts to depth, so we can check depth variability over time. And this is called a current tilt meter, which actually, when it's submerged, floats vertically and has an internal gyroscope that can actually access what its angle is as the flow is moving past it, and based on that angle can calculate a flow velocity. So we have a means to measure flow velocity and a means to measure water depth in the channel. So we placed a number of these paving stones in a bend segment, classic bend segment of the upstream channel reach. And this is what I'm showing you here. This dashed red line that you see is this particular bend segment here. We have 4 paving stones that were placed, so 4 positions of instrumentation. Upstream, in the bend section itself, I'll denote the inner bend is noted in blue here, the outer bend in red, and downstream here, which is this black point. So just keep that in mind, blue, inner bank, red, outer bank. So what we're gonna do now is look at velocity data across the time domain of our observational window. Flow speed is on the x-axis here from 0 to 1.5 meters per second. Time from March through to May is on the x-axis here. Excuse me, flow speed on the y-axis. What you note is that during low discharge conditions, relatively low flow speed, roughly 30 centimeters per second, the blue, which again is the inner bank, and the red, which is the outer bank, have a velocity structure that is consistent with what we know about other peat streams, namely the inverse of what we find for alluvial rivers. That is, the outer bank is slower than the inner bank. Okay, but when we go into our freshet period, which is shown quite distinctly here, where we get these high flow velocities because of the flooding conditions, you can notice that there's a swap between the high velocity core from the inner bank to the outer bank as the creek system floods its overbank, floods its floodplain, goes overbank. And so, interestingly enough, the hydrology of the system does a whole scale swap during a flood condition through which we have overbank flooding. And then once we get back into a background level here, and once we pursue into May here, once we come into May here, we see that we actually flip it back to the traditional peat stream design that is higher velocities on the inner bank and lower on the outer bank. Okay, so we have this swapping of the thalweg high velocity core, inner and outer bank for this peat stream during the flood condition. This is a gain camera time series images that were present at our collection site during this freshet period. So this will cycle through from about March into about April and just give you a general sense for what this looks like during the spring freshet and the flood period across our timescale of observation. So you can see, of course, winter, we have lots of snow, and then some turkeys that are moving around there. And then we get right here our flood, right? So everything floods at that point right there. So that is our freshet, and it's that period where we get the high velocity flood discharge conditions and the swapping of location of the high velocity core. Okay, we also pursued several coring strategies here. What we find is transects and locations of cores collected both upstream and downstream. These are 3-meter long, essentially pipes, aluminum pipes that have a diameter of 7.5 centimeters. We call them vibra cores because we have a backpack vibrator, which I was wearing right here. It's a concrete vibrator. It's used in the construction industry to set concrete onto rebar. In essence, what you do is you attach it to your 3-meter long aluminum pipe and drive it into the channel and or floodplain deposits. And you can collect this core and bring it out, open it up, and you can begin to examine what the subsurface composition is. I'll just note here, for our upstream cores, what we find is a lot of this black, and that black is just peat. What you see in these layers of sort of lighter color material, that's traditional inorganic sand. So that's what we find typically with alluvial systems. If you note the 3 cores that we've collected downstream that I present here, there's this mixing between both peat and sand here, and it looks as though this mixing is more prominent. So the sand is more prominent in the downstream than what we find in the upstream, and we'll see why that's important here momentarily. So if we look at what the upstream cores are showing us, what I've done here is just drawn an elevation profile across a point bar for the upstream transect. The water surface elevation is denoted here with this blue dashed line that you see. So this is the primary channel. The core that we collected in the channel here has just a smidgen of peat at the top, but in essence has sand that goes all the way down to its base. Okay. If we look at other locations in the upstream section, what we find is that away from the channel, we have in essence nothing but peat. So in the channel, loads of sand as far as we can collect this core, and everything outside of that seems to be peat. So if we couch this into the model of Candel that I showed prior, in essence, what we think we have here is a channel system and a peat system that are grading vertically so as to give you continuous sand in the channel and peat on the outside, which is consistent with our understanding of the aerial images that show no lateral migration of this channel. So in essence, this channel is stuck in place as is shown within the cores of peat, all in the floodplain, and sand in the channel system itself. If we take radiocarbon dating, we can constrain the rate of deposition, and this is on the order of 1/10 to 1/3 of a millimeter per year. So nicely within that window of the global compilation that I showed prior that shows about 1/10 to 1 millimeter per year in terms of peat deposition rates. Downstream is a completely different story. What we find is that the sand is intermixed with the peat, as we can see throughout these cores here. This is the primary channel that you see here. And so this sand itself is coarse material. It's the same grain size that one would find if you were to collect a sample from the channel itself here. So we think that these sands that you find, these embodiments of sand that you see here, are in fact representative of prior locations of the channel thalweg at some time in the distant past. So this is interesting of itself because it's wholly unique from the upstream location. The other piece that we can do with this is that if we assume that this sand here is reflective of channel sand deposits at some time in the past, we can take age constraints for organic matter within the sand itself, project the lateral distance of the channel at its former location to its current location and essentially divide that by the age of the sand deposit to come back out with a rate of lateral mobility, assuming that this system is then aggrading and migrating laterally across its floodplain system. So it's an independent method to check lateral mobility, at least in the downstream location where we think we observe lateral mobility against, in essence, the aerial imagery that I showed. So these estimates show lateral migration on the order of 4 to 11 millimeters per year, which gives us a timescale of migration for about 500 to 1300 years, which is inconsistent with the independent means that I showed prior, namely through the aerial imagery. Okay, so there's lateral migration, but I assert it's still boring. And the reason why is because if we look at migration rates versus channel width, for a collection of terrestrial fluvial systems all across Earth, what we find is that our peat streams here in Cedar Creek, Little Cedar Creek, Minnesota here, is still several orders of magnitude slower than what we find for comparatively sized systems that are fully alluvial in nature. So yes, there is some lateral mobility that we can observe and we can measure here, but it's nevertheless very much significant factor of 100 times slower than what we would expect based on the distribution of alluvial systems from across Earth. Okay, so again, very slow, but perhaps meaningful and important. The next step to the study is to adapt alluvial-based models to estimate channel migration. And you have to bear with me here. We're going to walk through a bit of numerical framing here. And this is the last piece that I'll show you here for this study. But in essence, what we want to do is calculate the rate of channel erosion, the sigma that we see here, and assume that it's equivalent to the lateral migration over a timescale of centuries to millennia. So fortunately, as I mentioned prior, there are loads of modeling frameworks that have been developed for alluvial systems. One of them describes erosion, channel erosion, as a function of stress applied on the bank line by the moving fluid to the stress necessary to actually liberate or move whatever is comprising that bank line, whether that be peat or inorganic sediment. And so we have some other dimensionless coefficients that go into this equation here. I won't go into the details of that. We're happy to discuss later if you'd like. We can calculate this tau bank, the stress applied to the bank line, as it's related to the boundary shear stress through this formulation here. We can calculate boundary shear stress based on the input data that we measure during our flood discharge conditions. So this is where velocity and flow depth become particularly important. And of course, we have constraints for that based on our measurements. So we have boundary stress, we have bank line stress applied. The question is how do we get this critical stress of mobility? And of course, there's loads of both empirical and theoretical frameworks that describe the physical basis behind calculating critical stress for a number of different entities, whether that be sand or mud or peat itself. So when we run through this modeling framework, what we describe is that the boundary stress on the bank line calculated for low to flood flow conditions ranges by about a factor of 10, maybe 15 here. So, right, we have about 0.03 pascals during low discharge, up to about a half a pascal during flood flow events. The problem is that the critical stress of mobility is roughly 1,000 times greater for peat than what is applied to the bank line. Okay, so that gives us a sense for why there's an expectation for no movement of the channel in the upstream region. Simply put, you don't have enough stress to liberate and move that peat, so everything's stuck in place. The only thing you have is vertical aggradation, as our core showed. Okay, this implies that the stress applied at high flow conditions is insufficient to erode peat. However, the critical stress of mobility for sand, that is the sand that we find in the channel and in the cores, is something on the order of 0.27 to 0.34 pascals. So this would be for 250 to 500 micron sand. So right away, we can see that during flood conditions, we exceed the critical stress and mobility for sand. So maybe we're onto something here. This indicates that sand is readily transported during flood events. if we use the critical stress and mobility of sand in our modeling framework that I provided in the previous slide, we calculate a migration rate of 9 millimeters per year, which gives us a channel migration timescale of 600 years, which again is entirely consistent with the two independent methods that we produced for calculating channel migration, namely the radiocarbon dating, which gave us 490 to 1280 for a channel scale or migration scale, and the imagery analysis through the photographs, which gives us 500 to 1,000 years. So the point here is using this framework, this physics-based framework that describes lateral mobility of an alluvial channel system, we get results that are consistent with two independent methods that are used to calculate channel migration of this system. But this is for a particular reach, that is the downstream reach, where we know we have this mixture of sand and peat. So we breathe a little bit of a sigh of relief here, because what it indicates is that we can possibly leverage previously defined models into peat systems, so long as there is sediment within that peat system itself. Okay, this is the last bit, and then I'm done here, I promise. The implications, hypotheses, and ongoing work. Sand is intermixed with peat to form bankline or floodplain material, and the sand is eroded so as to destabilize peat deposits. This is our working hypothesis at this point. In the downstream reach, in essence, you have, as our cores show, this interlayered mixing of both peat and sand. And where the channel itself, in the flood flow in particular, can route and mobilize sand, erode that sand, it can, in essence, get into a sand layer, transport that sand out, and undercut the overlying peat deposit, which we hypothesize is what's creating sort of a failure condition of that peat, and then allowing the channel to widen. In essence, that erosion of the bank line allows the channel to step laterally across its floodplain. But you have to have this intermixed sand and peat. That's the starting point. The problem is that we're left with the chicken and the egg conundrum, and that is, how did the sand get there in the first place? So what we know from traditional alluvial river systems is that to integrate sand into the floodplain, the most appropriate way to do it is to allow for the channel to migrate laterally across its floodplain, thereby building point bars that are subsequently buried through overbank deposits. But without having sand there to begin with, you can't migrate the channel. So we have this bit of a conundrum. Once you can trigger mobility, yes, you can incorporate sand into the floodplain deposits, but without the sand being there in the first place, you can't have the channel mobilize. So this is where we're stuck at this point, this chicken and the egg situation. Presumably, proximity of the channel to the source is necessary to introduce inorganic material. What I mean by this is that the channel does indeed interact with these bounding bluffs that are comprised of inorganic sediment. Presumably, that's where that sediment is being introduced into the system so as to incorporate it into the floodplain deposits. But how do we deposit sand on the floodplain? An obvious choice would be overbank deposition. That is, during floods, we suspend that sand into the water column, and then when that sediment-laden water goes over its floodplain, as I showed it does in the video images that showed the freshet flooding the floodplain, it can put down a layer of sand that can be included into the floodplain deposit. The problem with that is that the material that we're suspending is significantly finer than the median grain size that we find on the bed itself. And so what we've done is actually shown what the grain size distribution is for those overbank deposits, which we collected after our spring freshet. And if we look at how we should compare that to both a sand bed model versus an overbank model, versus a mud model, is that it looks like it's a mixture of both buds and sands, but it's still the finer fraction of the material that's being introduced to the floodplain. It's not this coarse 250 to 500 micron sand that we find in the floodplain deposits in the lower channel reach. So it seems as though this idea of presenting sand into the floodplain through overbank deposition is a non-starting point. So we're back to our chicken and the egg situation. So we're not really sure how we trigger lateral mobility. This is the point that we're at right now, and we need to crack this nut because we have to resolve this in order to describe how changing channel hydrology, which we can predict, so we can work with our atmospheric sciences colleagues and our climate colleagues to understand how this region should expect to experience changing hydrology as a function of climate change. We can use that as an input parameter into our modeling framework that we know works for describing lateral mobility of the channel system. Presumably a greater hydrology through intensified hydrological conditions would access more sediment adjacent bluffs and introduce that into the floodplain itself. But until we can actually model this, it's not possible to actually say how changing hydrology will impact the mobility of the channel system. Okay, so just a couple quick conclusions here. Key factor for controlling channel migration in peatland streams is the presence of inorganic sediment. In essence, you have to remove that sand from the bank line itself to create a condition that undercuts the peat and collapses the peat into the channel. The second here is that the introduction of sand in the system is a function of proximity to the bounding glacial bluffs, as well as a hydrological cycle where presumably flood conditions access that sand and bring it into the channel and floodplain system. Lateral migration of the channel is enhanced. The effectiveness of peat systems to sequester organic carbon diminishes. And this is because, as I described earlier, as it migrates laterally more effectively, it's liberating rather than sequestering peat. And therefore, the exchange with the atmosphere would be sort of one-way direction toward the atmosphere. So questions abound about how we move coarse sand into the floodplain deposits. And this is subject of ongoing and future work. So thank you for your patience, and I'm happy to take questions.